Thanks very much. I'm Andy Keep, and following in my office mate Will Bird's tradition, I'm not going to show any Clojure code today. Sorry, but I will show some Scheme code. I wanted to start by saying I'm Andy Keep, and I love compilers. And I love writing compilers and doing things with compilers. I think it's a lot of fun. So I wanted to start out with a little bit of compiler history, just to talk about what the idea of the Nanopass stuff was and what the genesis for it is. So we used to write compilers as just a handful of passes. For convenience here, I've only represented 3 passes. Most of those compilers had more than that, but not too many more than that. And the early compilers were written this way because each individual pass had some work that it needed to do, but there weren't enough resources on the machine to necessarily do that all in a single pass. And in fact, there wasn't even enough resources on the machine to store all this stuff in memory. Each pass would actually read in a representation of the program, write it to the file system. The next pass would read it in and write it to the file system. And so you can see why they wanted to minimize the number of passes that they had in their compilers, especially when the file system was a tape drive or paper tape. So, not a great design, or not a great space to be able to do this stuff in. But computers got better. And then we could do our same handful of passes and we could keep everything in memory. And that was kind of nice, but people continue to write their compilers sort of this way. I mean, there are some exceptions. Some things were written with many passes, but for the most part, it stayed this way. And sometimes we even never write it to the file system. We just go ahead and run it. That's pretty cool. This is sort of the situation when you're at the REPL in something like Scheme or Clojure or Haskell or ML or whatever your favorite REPL is. To talk a little bit about the compiler that I worked on, a single pass did Clojure conversion, loop recognition. It began our handling. It handled multiple return values, foreign callable handling, foreign function handling, direct call optimizations, and then Clojure optimizations started in one pass and then continued in the next pass. And the thing that makes this all kind of tricky is that if I'm sort of actively working on my compiler and I want to add a new optimization, and that new optimization has to happen after one task, but before another task, and both of those tasks are performed by the same pass, well, now I'm sort of in trouble because I have to find a way to kind of weave that into the existing pass without breaking anything that's already there. And so that's pretty tricky. So what we sort of want to do is we want to take these things and break them up into a bunch of small passes where each one of these passes is just performing some single task and then run through them that way. So as I said, I love compilers, but I particularly love Nanopass compilers. And I've spent some time working on this stuff. So just to give you a little background on where the Nanopass stuff comes from, this all grew out of the compiler class at Indiana University, or at least had some of its genesis there. So my advisor, Kent Dybvig, who was at Indiana at the time, had gone on sabbatical, I think. And Dan Friedman taught the course. And he really wanted to get away from this sort of teaching of passes, these big passes, and building a compiler. And he wanted to talk specifically about what are the ideas, the interesting ideas in the compiler, and how can we get students to go through them in a way that they'll more easily understand them. And so he came up with this idea of writing these passes that were very simple, just did a single task using like a pattern matcher, and introduced this idea of playing the game, where you handed in some piece of, something that looked maybe a little bit like Scheme, and you got something out that maybe looked a little bit like Scheme but had been transformed. But you could evaluate the input and you could evaluate the output, and you could see that both of them were the same. And he called this playing the game. And so we still do this in the IU compiler class. Now, that particular year, my understanding at least, is that the compiler sort of wasn't a compiler as much as it was a set of disconnected passes. So the ideas got across, but they never built a full compiler. So when my advisor, Kent Dybvig, got back and started doing this class, he said, here's a good idea, but we have to have the students build a compiler, of course. And so the result was a compiler that was around 40-some passes that the students wrote over the course of the semester. And it compiled a subset of Scheme down to assembly code and implemented things like a graph coloring register allocator and fun algorithms like that. And the whole thing was written with match, and the representation that we used for the compiler were lists. So we're doing match over lists, and this was good. It worked pretty well, but there were a couple of downsides. The compiler was a bit slow, partially because of some of the pattern matching overhead. I don't have it on the slide, but the other sort of downside of this was that you might have a pass that produced ill-formed output, and the next few passes accepted it because they didn't know any better, or they didn't do anything that impacted it. And then you'd have a pass fail that was 5, 6, 7 passes down the line, and you would think, this 10th pass in my compiler must be wrong because it's where the error occurs. But the problem wasn't there. The problem was actually 5 or 6 passes ago when you had this malformed result. And so the idea was then to create a Nanopass framework to try and address some of this. And so the Nanopass framework was originally prototyped by Kent, a fellow named Oscar Waddell, and primarily by Deepa Sarkar. And they put together a framework. They wrote a paper about it. They sent the paper off. They said, we have this technique for doing educational compilers and commercial compilers. And they sent it to the ICFP, the International Conference on Functional Programming, and they said, no, we don't believe that you can do a commercial compiler with this. We think you have to refocus the paper to just say educational compilers. So that was the Nanopass, the idea behind the Nanopass framework and sort of its first iteration. Some of the details of the Nanopass framework, we have formal language grammars. So we define the syntax of each of our intermediate representations between each of our passes. This gives us the ability to check that information as we go along. We then define passes over these grammars. So we're able to create these passes and make sure that they have a formal input and formal output language. When I say formal here, I'm just talking about a grammar syntax and not a semantics. And then we made it easy for languages to be extended. So we wanted to be able to make very small changes and have lots of languages in addition to having lots of passes. And this let us sort of express these tiny changes as we were going along. And the pass form itself can generate some of the boilerplate code that we otherwise would have had to write doing all of these sort of micro passes using the match system. So we have two forms, main forms in the language. Define language, which we use for defining our languages, and define pass, which we use for defining passes. To this, I've added a couple of other forms with output language that allows us to create language forms outside of a pass, and Nanopass case, which allows us to match language forms outside of a pass. So the idea there being that sometimes we need to sort of separate the two things that the pass does, reading and constructing language forms. So all this machinery gives us some benefits. First, it allows us to auto-generate some of the pass clauses. So because we know the input language and we know the output language and we know how they're different, we also know how they're the same. And so for those things that are the same, we can auto-generate things like recurring through forms that are otherwise not changing but might contain some changing form. It also allows us to choose a more efficient representation than lists. So in Scheme, we don't have some of the fancy data types that you guys have in Clojure, but we do have records, and we can use the records to make things more efficient by making a decision about what pattern we've hit just looking at the record and not needing to sort of traverse the whole list to decide whether or not we've hit a pattern match. It also allows the framework to check that output from each pass is going to be well-formed. And so now, if our pass is producing something that doesn't match the syntax, we know for sure immediately that that's not going to meet the syntax, and we can raise an error right away. And hopefully a student or a commercial compiler writer that runs into this can fix it much earlier on. So as an aside, we decided that we wanted to take up this challenge of a commercial Nanopass compiler. And we did this in the context of Chez Scheme, which is my advisor's Scheme compiler. And we took his compiler and we decided we were going to write a commercial Nanopass compiler. So His original compiler looked something like this when I first started working on it. It had about 11 passes, 6 front-end passes, one that was optionally run with the source optimizer, that's this guy in the middle here, which, again, my laser pointer doesn't actually seem to show up, but oh well. We sort of kept the same front end, and we kind of exploded the back end, just a bit. So just so I can spare you counting, there are 52 passes now in the back end. So we went from 5 to 52, and we added this loop here in the back end as well, where we're doing graph color and register allocation, which gave us some benefits in terms of the performance of the code that we compile, but did slow down the compiler a bit. Just to give you an idea, though, of the order of time that we're talking about, when I started, the Chez Scheme compiler could compile itself in about 3 seconds. So tens of thousands of lines of code, roughly, in about 3 seconds. Well, okay, to be fair, I haven't counted. But it's a significant amount of code, and it does it in about 3 seconds. The new compiler currently will compile itself in about 10 seconds. So it's still very, very fast, even though it's doing a lot more, going through a lot more passes. And sort of the idea here is that it's not the number of passes that impacts it as much as it is that you have some passes in there that are just more expensive, and they tend to dominate the amount of time that you spend. So the overall compile time is only about slower by half. But as much code as we had before, our macros now that we use to define these languages and these passes generate a lot more code. So with all of that said, I thought it would be interesting for us to look at an example. And I did a little bit of a stupid thing. I was going to talk about the class compiler that we have at IU, but I sort of didn't want to put that code out on GitHub and share it because we have students still taking that class, and I would sort of feel bad if, one, they downloaded it and turned it in as their assignments because they wouldn't get the benefit of actually learning it, and the fellow that's teaching the class right now would actually have to try and find all those cases, and it wouldn't work out well. So I decided Monday afternoon that I would write a new compiler, and it's available on GitHub. I haven't slept much in the last few days, but it's available on GitHub. And we're also going to compile a subset of Scheme. Just some parts of Scheme here. We're going to represent our variables as symbols. Not surprising, this is how we represent them in Scheme as well. We're going to have a handful of constants, true, hash t, false, hash f, nil or null, and 61-bit integers. And I'll tell you why 61-bit signed integers in a few minutes. And then we're going to implement a handful of primitives. So char, cdr, cons, pair, and null for dealing with lists and pairs, Boolean question mark, make vector, vector ref, vector set bang, vector question mark, vector length, box, unbox, and box set, which is not something that we have the students implement, but we're going to use it for something. You'll notice that I didn't put set char or set cdr in there, so my lists are immutable. We've got plus, minus, times, divide, equal. Those are all going to operate over our 61-bit integers. The other comparison operators, and then EQ, which we're going to use for sort of identifying whether something is the identity, right? So is this thing exactly that thing in memory? And we also have quoted datum, so we can define constants. We can define quoted pairs, which then can contain more datum. And then this funny thing here with the hash is how we represent vectors in Scheme. So we're going to use this to represent vectors, which are basically just fixed length arrays. Okay, so I said that we had a formal language for defining these things in the Nanopass framework. So of course, we have a source language. And we can define that in using the Nanopass framework here. So we have a set of terminals. And part of how we know that our languages are well formed is each of these terminals corresponds to a predicate. So Scheme has a predicate called symbol question mark. We're going to use that for recognizing our variables. The primitives I wrote my own predicate for. Constants I have my own predicate for, and datum I have my own predicate for to check these things. But this is going to allow the Nanopass framework to check to make sure that when we construct a new language form, all of the parts of it are of the correct type. Then we have a set of productions that are the expressions in our language. So the first few productions here are standalone primitives, references to variables, and standalone constants, and quoted datum. So these all look like S expressions, but underneath all of this, we're going to create records for anything that's structured. So this quoted thing here, there's actually going to be a record created for it with one field. Then we have our branching things, if, one-armed if, two-armed if, or, and not. And of course, we could implement or, and not as macros, but our language doesn't have macros yet. So we have to actually define those as compiler passes. And the dot, dot, dot here just means we're going to have 0 or more of these things. So or has to have 0 or more elements, and has to have 0 or more elements. And these, of course, are each going to get a record associated with them as well. And then finally, we have setbang, mostly because I just think assignment conversion is kind of fun. I don't have any particular love of setbang. But then we'll have begin so that we can do more than one thing in our ifs, let rec, and lambda, and of course function application. And the square brackets here, they mean the same thing as the round brackets. We just use them so that we don't get confused when we see the bindings. So I'm sorry if it's a little confusing. I know that Clojure uses these to mean different things. Scheme's a little bit, yeah, everything's a parenthesis in Scheme. So our target language for this is going to be C. Now normally, I target assembly, but again, I did start this Monday afternoon, and I felt like, writing the register allocator, while it's a lot of fun, also tends to be a little bit of work, particularly remembering how to get it right. And I wrote some of this on the plane. I knew I wouldn't have reference to everything that I needed, so I decided to do it in C, mostly so that it will do the register allocation for us. I went home Monday afternoon and I wrote a bunch of code, and then I got on a plane and I wrote a bunch of code, and then I kind of finished up the last details of this over the last couple of days. And I got a compiler that looks a bit like this. Again, to spare you the counting, there are 27 passes here. And this takes us from our source scheme language down to C, and we generate C code. And just to zoom in a little bit, the first thing that we're going to do is sort of parse and rename. And it's a little unfair to say parse. We call this parsing in Scheme, but really we're going to use a Scheme reader to do the real from string parsing. And we're going to use S expressions and turn them into our internal record representation. And we're also going to rename variables so that once they're in the compiler, they're always unique. That's helpful for us because then we don't have to worry about that later. Then we've got some steps that are just going to simplify things. We're going to remove our one-armed if. We're going to remove and, or, and not. We're going to make the begins explicit in the bodies of our let rec, and lambda. We're going to inverse eta raw primitives, which is a really fancy way of saying that when we see a primitive standing by itself, we're going to wrap a lambda around it with the proper number of arguments, and we're going to call it. And this is mostly just so that we can move all of our primitives into call position so that we can do what's called open coding them. In other words, we're going to generate the C code to do those directly rather than having some function that we're going to call for the primitives. Then we're going to quote our constants, remove our complex constants. So where we have structured constants, we're going to make their allocation explicit. And we're going to identify the assigned variables so that we can do assignment conversion. And we're going to turn our letrecs into things that bind only labels to lambdas. Optimized direct calls is just a way of looking for directly applied lambdas and turning them into lets. We're going to find our let-bound lambdas and turn those into letrecs. We like letrecs. They're pure and fun to deal with. We're going to remove our anonymous lambdas, and we're going to convert assignments, and that's going to get rid of setbang for us. So by the time we're done with that, everything will be either an immutable variable or a data structure that has some way to mutate it. Then we're going to uncover free variables, convert closures. We need to do this in order to sort of drop this stuff into C where we don't have closures available to us. Well, okay, I know that there are now sort of lambdas in at least the newest C standard, but we're not going to use them. And then we're going to optimize known calls, which is basically a way of saying we're going to make the function call, rather than pulling it out of the closure, we're going to just call it directly. We'll lift the lambdas, get rid of nested things, nested expressions. We'll separate things into contexts. I won't go into all that detail. Expose the allocation primitives is going to basically start to convert
some of our stuff into something that looks closer to C. We're going to reintroduce set bang. We're going to get rid of let. We're going to flatten those so that we never have a set bang that's on the other side of a set bang. And then we're going to push our ifs in, which I think we need to do for C just to get all of the predicates in the same place. We're going to specify a constant representation. This is part of why we have the 61-bit integers. And we're going to expand primitives and finally generate C, which is a lot of stuff. So first, let's start by looking at the second language in our compiler. So there are 23 languages total. L source, admittedly the only named language, and then a whole bunch of unnamed languages that have been conveniently enumerated as L1 through L22. Yeah, sometimes it's hard to come up with meaningful names for these things. The basic idea here is that we're making a very small change. We're going to extend our list of primitives to add void, and we're going to get rid of our one-armed ifs here. And so that's going to be the technique. And we're going to look at one pass here in detail. So this is the very first pass. It's not too much code to write, actually. It's just this kind of one-line clause and some of the context to wrap around it. So when we define a new pass, we're going to get a new function named removed one-armed if. This is our name. And then we have a signature associated with it. And the signature tells us what our input language is, what our argument list is. So this one accepts one argument, and it's an argument of the L source type. And then we're going to have an output language, and we're going to output the one thing, the language thing. And Scheme has multiple return values, so we have a way of returning multiple things, but we're not going to return anything else here, so we can indicate that by just having these empty parens here. And then we're going to have a transformer. And the transformer here is just this piece. The framework figures out what transformer it should call automatically. And the transformer we can name. We tend to name it the same as the non-terminal that we're processing. But you can choose any name you like. We just have sort of done that as a standard. And then we indicate what the input non-terminal is, what its argument count is, what the output non-terminal is, and any extra values that we want to return. And then within the body of our transformer, we're going to match some clause and take a look to see what it is. So we've got an if here, the one-armed if that we were trying to match. The little commas here, these are Scheme's version of unquote. So the tilde that's used in Clojure, this is the Scheme equivalent of. And then our square bracketed things here, this is actually to indicate what's called a catamorphism. The idea behind the catamorphism is really fancy category theory stuff. I think of it as I recur on something that's smaller than the thing that I had before, which I think is more or less the definition. So what this is basically going to generate for us is a call to expr. So it's going to generate the value of E0 by calling expr on the thing that it found and making that available in the body. So we really don't have to do too much fancy. Really, the work that we're doing here is to add this void so that we have a two-armed if instead of one-armed if. So here, the quasi-quote, even for those of you familiar with Scheme, is maybe going to be a little bit misleading. Quasi-quote does not do what you expect it to do here, because it's not building a list. It's actually building a record for this particular type. We made use of the fact that we have the flexibility in the macro system to override what quasi-quote means in this context. Which is nice because it means that we can sort of take our old match-based compilers and we can just kind of translate them pretty easily. But it's a little confusing for people when they first see this stuff. And then, of course, we have our quotes again. Again, this is our unquote. And our void. And here, we are actually building a record for the primitive call, or for the call here. And the primitive is just the quoted symbol void, which we don't have to do the unquote and quote around, but I think in Clojure you do have to do the unquote and quote around to get that piece working. So pretty simple, actually. But this really isn't all this pass needs to do, because there are many, many other forms in this language that need to be recurred through. And so this is one of the great things about the Nanopass. It actually is going to generate for us all these other clauses that we don't need to worry about.
And if it finds a clause that it can't figure out how to build, it will either, well, okay, let's see. Does it ever complain at compile time? I don't think it ever complains at compile time, although it probably could in some situations. But what it does do, because I got sick of trying to debug this while we were working on the Chez Scheme compiler, is it puts an error message in there that remembers the source location of where things may have gone wrong and reports back, hey, something went wrong at this source location, which is kind of nice when you're trying to debug things, especially if you spend about 18 months working on a compiler, and it turns out you run into these things more frequently than you would like. Because you forget to write some clause that you needed to write. Okay, so let's talk about the representation. I said I would say why we had 16-bit signed integers, 61-bit signed integers. So the whole reason behind this is because scheme objects are going to be word aligned. We're going to kind of play a little bit of a game here and represent all of our scheme objects with just a word size 64-bit pointer. Because they're word aligned, it means that the bottom 3 bits are always going to be 0. So, hating to waste anything that we could use, we're going to use those bottom 3 bits in order to tag the types of our pointers. So these bottom 3 bits are going to give us a tag for pairs, vectors, boxes, closures, and actually for fixed nums, which is why we have our 61-bit signed integers, we're actually going to use raw pointers to represent them, where the tag on them is just going to be 0. It turns out that works out well for the math, and we can identify them fairly easily. So what about representing closures? Because I said, we don't have closures in C, and there's a number of different ways we could have decided to do this, but I decided to sort of follow the model that I'm most familiar with, partially because I was running a little bit on trying to get these all put together. So we're going to use what's called a flat closure representation. With a flat closure, there is one slot for the code pointer and one slot for each of the free variables that's needed. So just to give you an idea of what that looks like, let's imagine we have these nested lambdas here. And we want to figure out what the closure looks like for the innermost lambda. So we do a free variable analysis, and we figure out that x and y are free variables in the innermost lambda. Because they aren't arguments, they actually come from the outer lambdas here. So when we create a closure for the innermost lambda, we need to have one code slot and 2 data slots, one for the x and one for the y. And that's how we're going to represent things internally. So what about C? How are we going to represent all of this in C? And one approach that we could have taken is to represent our closures by building new data structures that represented each closure. We could represent our pairs and boxes and things like that as data structures. But I don't like to do that kind of stuff. Admittedly, some of this is because I'm used to generating assembly, and I kind of like to play with the low-level representations. So we're just not going to tell C what we're doing at all. Because you know what? C really doesn't care. C is happy to do whatever you want with a pointer, and that's what we're going to do. So maybe not the safest C code. We're going to have to trust our compiler is going to generate the right stuff. So instead, what we're going to do is we're going to just play with the memory directly. When we need space, we'll allocate some space. When we represent a fixed num, that'll just be in a pointer. So with all of that said, let's take a look at this, and let me adjust my screen here. This works out so much better if the displays are mirrored. All right, so yeah, copyright. I put that in there mostly just so that I can put like an MIT copyright on these things, MIT style or BSD style copyright. So this is all the stuff. This is what's out there on the GitHub, actually. These are all the random things we're exporting. The important thing from our export list is we've built this as a little library, and we have the main entry function, mytinycompile, which is going to compile things for us using GCC as the backend, and actually reread the value. We're actually going to do everything from inside Scheme so that we don't have to actually touch C. That would be nasty. And then we can trace our passes and see what it's actually doing. I took like 10 minutes and looked up the Bohm garbage collector to see if I could get a garbage collector running, but I sort of ran out of time to test it. So you can actually turn this on, and in theory, it should generate code that will use the Bohm collector, but in practice, may not. Okay, so we have a representation for our data types. And so the fixnum tag is just 0. We have our pair tag is 1, 2 for our box tag, 3 for our vector tag, 4 for our Clojure tag. We have more tags that we could use, but we have a representation for our true and our false values, a little tag for Boolean just to make Boolean question mark a little simpler, and a record for our fixnum shift here, so that we know that we need to shift the thing 3 bits up when we want to make a change to it, or 3 bits down after we've done operations like multiply and divide. And our word size, just so that we know that we've got 8 bytes here in each of our words. And then we've got some stuff here for taking care of like unique variables and our list of primitives, which should all be cleaned up. My to-do here, which didn't actually get done. Ooh, and my misspelling of should. Sad. All right. And then we have a number of language definitions. So you can kind of look through these. I actually included a potentially out-of-date comment with the full language in here, but most of these languages are generated this way. And they can actually be regenerated by loading the library and loading the Nanopass framework and then just saying language arrow s expression, and it will give you the full language definition. And then we have all of our passes. So the first pass, the parse and rename pass, yeah, it's a little long, which is why I didn't end up talking about it. We're doing something that's a little bit macro expandy here, in that we're defining this initial environment, and this is really all I wanted to show from this. So because we're in Scheme, our keywords can be overwritten, and we need to have an environment as we read in the code to know which thing we're actually referring to. So we want to make sure that if someone binds a variable called quote, we don't then see all of the calls to quote as quotes. So we use an initial environment, and then as we rebind new things, we just extend the environment. And that's the idea there. So since I'm running a little short on time here, let's actually take a look at this example code here. So I intentionally shrank my history so that I'd only have a few things in here. So I cheated a little bit. So we're going to import this, and it is a little bit slow to import. There's a couple thousand lines of code that's actually in our compiler itself. Plus there's all the Nanopass code, and then the Nanopass code generates a whole heck of a lot of code. So we tend to get a little bit of slowdown there. But let's do our first tiny little program. Originally, I was just going to test this for 2 programs and make sure that those 2 programs worked, the program 5 and factorial. So let's test the program 5. Okay, so that worked. That was good. It compiled 5 through all 27 passes. It wrote a C file to the file system. It told the C compiler to compile it. It ran the program. The program output was written to the file system, and then we used a scheme reader to read that back in. That's what happened there. Thanks. Okay, so we have our other program, factorial, and we're going to run factorial of 10 because this is a compiler. There's no reason for us to limit ourselves to 5. It's also reasonably fast, so that's our answer there. And I know it might seem like, hey, how do I know that you're actually doing anything here? So we're going to turn on our trace passes, and we'll run the same program again. Okay, that actually went by too fast. This is the stuff that it generated. Okay, all right, we're somewhere around the start here. So you can see, we start running our initial pass here, parse and rename, and then we run our remove one-armed if. And some of these passes aren't going to do anything, really. They're just going to recur through the code and generate the exact same thing that came in because none of those pieces are actually there. We don't need to do anything with those things. But there are certain parts that are going to do transforms, and as we get through this whole thing, we're eventually going to get to some C code. The C code is also entirely generated from inside Scheme.
So if you go and look at the code, there's a bunch of printfs that printfs in order to do this stuff. This was less fun to write, by the way. This is the downside of not using the data structures that C provides, is that you end up doing things like casting to a long a reference of a pointer that you cast to a long to do the math on the pointer. Okay, so you have an idea of what's going on here now, and let's go back to the slides for a second. Okay, so we have a little compiler. What else can we do, right? I mean, it does a little thing, and it runs at least 2 programs. I actually did test it on some other programs, and I fixed my vector representation for those people who I was talking to, and I had a broken vector representation. But one of the things we could do is add a different backend. I mean, you know, C is a fine target for us, but we could also target, you know, JavaScript or Clojure or the JVM or .NET, whatever we want, really. LLVM, I've really been wanting to play with LLVM, but I haven't had a chance to yet, so that would be a fun one. We could also add more primitives and data types. You know, there's a lot of data types that I think are really neat in Clojure that I would love to add to a Scheme implementation so that I can use them in a Scheme implementation. Of course, I should probably also, you know, use some Clojure. We could also add more optimizations, and of course, this is my favorite thing to do because part of the reason why I love compilers is I love fast, and these are to make things fast. And we could add more runtime factors, like GC, which may or may not work. But we could also add things like foreign function calls and things like that. Another thing is we could port it to Clojure. I would love to port it to Clojure. Sadly, I don't know Clojure yet, but it's on my list of things to do. And we could do a couple of things here. We could port compiler using just core match, sort of the internal representation. I suspect this would be faster than our match. This, I think, would be the easier task. The other piece is we could actually port the framework to use Clojure macros and to use a more Clojure-like syntax and to feel generally more Clojure-y. I think this is going to be a bit harder. Harder partially because right now the entire thing is written using these gigantic syntax case macros, which is part of the reason why I know that we can do arbitrary computation with syntax case, because believe me, I do arbitrary computation. But you know, there's nothing missing for us doing this. It's just the work of getting it done and figuring out how all the pieces fit together. And with that, I'd like to say thanks. I have a ton of links here: the compiler, the framework, my email. If that's the one to remember, if you get lost on everything else, because I can respond with everything else. The Twitter, which I suppose is also useful because I can also respond on that one. My webpage where I will post this stuff, and then this stuff runs on Chez Scheme. Unfortunately, the Scheme compilers, they are not all so close together. I think it should run on Icarus and Vicari, although I have not yet tested it on those platforms, but it should be supported on those. And I think I have just like a minute for questions. And I can't see very well, so if someone has a question.
Yeah, quick question over here.
Yeah.
So awesome work, obviously.
Thanks.
We need to, you know, work it back. I'm curious if you'd explored the idea if thinking of passes as relations instead of functions, and if there's, you know, leverage there in terms of doing things like optimizing for code size or other parameters.
Yeah, so I haven't thought about it in quite that way. I do sit next to Will Bird, so we have actually talked about some of the ideas, somewhat in the context of actually like writing a type checker that you write with a pass like this that is actually written in a relational style. And many of the passes are written in a relational style. In fact, the if that you saw could have been done as a relational thing, right? It's just a term rewriting at that point. And like any term rewriting, it could be done relationally. So, yeah.
What do you do about passes that have a lot more output than NAS2, like somebody produces a control flow graph or some other sort of global analysis?
Yeah. So we produce a control flow graph. So passes actually don't have to produce an AST. They can produce things of different types. And what we used to do was we sort of produced an AST that had the information about the control flow graph embedded in it. It turns out that's not necessarily the best way to write your register allocator. So what we did instead was have it generate the graph for us, and then the graph gets passed through a couple of
graph-oriented passes, and then it gets turned back into an AST when we're done with that process. So, the idea behind this framework is to write these little passes because we can write these little passes, but we can't always write these little passes. So, in particular, like the Chez Source Optimizer doesn't use this style of these tiny passes because the things that it does in order to get the performance that it gets, it combines several different optimizations at the same time that are mutually beneficial. And so it's actually quite a big pass, even though it's using the Nanopass framework to build it. So you're never limited. This is more to enable you to write more in this style. So, and I think I'm past out of time, so I'll leave the rest of the questions for after. Thank you.